My name is Walter Hartwell White. I live at 308 Negra Arroyo Lane, Albuquerque, New Mexico, 87104. To all law enforcement entities, this is not an admission of guilt. I am speaking to my family now. Skylar, you are the love of my life. I hope you know that. Walter Jr., you're my big man. There are going to be some things that you'll come to learn about me in the next few days. I just want you to know that no matter how it may look, I only had you in my heart. Goodbye.
I don't think I need to tell you my name, as I think you know what my name is. Now today, we will be talking about chemistry. So just what is chemistry? Well, technically, chemistry is the study of matter. But I prefer to think of it as the study of change. Just think about it. Electrons change their energy levels. Molecules change their bonds. Elements combine and change into compounds. But that's all of life, right? It's the constant. It's the cycle. It's solution, dissolution, over and over and over again. Growth, then decay, then transformation. It is fascinating, really. So today, we're going to be taking a look at chemical reactions. And we're just going to start with some basic introductory material. Let's start first by going over what we've learned about physical and chemical changes in chemistry. We talked about chemistry being the study of change and how matter undergoes this change. Now, matter can undergo physical change when it changes in size, for example, or shape, or perhaps changing its state of matter from a solid, becoming a liquid, then a gas, or back. Now, when it comes to a chemical reaction, though, there are specific signs that we look for. And you will see more than one of these in every chemical reaction. Color change. Now keep in mind, a color change alone may not indicate a chemical change, but this, along with one of these others like heat or light being produced, is a sign or an indicator that a chemical change has in fact occurred. You may see a gas produced. Usually that means you will smell something. So always wear your proper protective equipment. And in some cases, you have two liquids combining, and they may form what's called a precipitate or a solid. Overall, in a chemical reaction, a new substance forms. And then you have the product. So let's go over a few vocab terms before we move any further. We discussed the precipitate, which is one of the reactants, or one of the indicators that a chemical change has occurred, one of the products of a chemical change. So what is it exactly? A precipitate is that insoluble solid that forms in a chemical reaction. Insoluble, remember, means that it does not dissolve in water. Here are some images that illustrate what you might see with a precipitate. You might see a white cloudiness or a nice yellow color in some cases, and it may not appear solid, but if you were to spin it in a centrifuge, as you can see here, it does settle to the bottom and collect as that solid. We also have certain prefixes we're going to use, like exo, like exiting, means release. Endo, like when things enter, means absorb. Just think about biology when you learned about the exoskeleton of the insect and the endoskeleton of the human. One means out, one means in. You're going to see some root words like gonic, which refers to energy, and thermic, like thermometer, which refers to heat or temperature. Now, if we put some of these terms together, you'll get words like exergonic, a reaction that releases energy. When you get this term endergonic, just the opposite. It's a reaction that absorbs energy. Exothermic, as you could now put together, means a release of energy in the form of heat. So endothermic means an absorption of energy. Now be cautious when working with these two terms because they can mislead you. Something endothermic absorbs heat. Well, you might think if it's absorbing heat, it's getting hotter. But if you were to touch a reaction or feel the atmosphere around the reaction of an endothermic reaction, if it's absorbing heat, then it's taking your heat away, and you therefore experience a cooler temperature. Obviously, if you were to be around an exothermic reaction and it's releasing heat, you're then going to feel the heat it releases. So we differentiate these by remembering that exothermic reactions would feel warm or hot, or raise the temperature of a thermometer, and endothermic reactions would feel cold or lower that temperature. Now when we look at chemical equations, we have a beginning and an end. Here we're just using A and B as a generic beginning and C and D as our generic end. A and B represent the reactants. That's what you start with in a chemical reaction. And it's very important that you follow the steps precisely because you want to get a very pure product. The product is what you end the chemical reaction with. And I guarantee you that I can produce the purest product there is. So what you see is before the arrow, that's everything going into the reaction called your reactants. And after the arrow, you see everything coming out of the reaction called your products. So here's an example. You can see we have flour, eggs, and milk. Those would be your reactants. They're what going into the reaction. And then it undergoes a chemical reaction. You see a color change, perhaps. You see a temperature change. You even smell it. The gas is being produced. And so you know a chemical reaction is occurring. And then your end product is this cake. Delicious. Now here is a reaction written out. 2H2 plus O2 yields 2H2O. So what are your reactants? Well, we can see the reactants are H2 and O2, which represent hydrogen and oxygen. And the product is water, H2O. So let's look at how some of these symbols are read, or how you need to understand them. The plus sign means reacts with, or plus, or and. The arrow can be read as it produces, or it yields, or forms, or reacts. S, L, and G refer to the state of matter or the phase of matter. Is it a solid, a liquid, or a gas? Now AQ, think aqua, which you know means water, and the term is aqueous, which means it's dissolved in water. So looking back at this reaction we just saw, we see we have 2 hydrogen gas plus oxygen gas produces or yields 2 water in the form of liquid. Now let's take a look at what's called the coefficient. Just like in math, it's that whole number placed in front, and in this case in front of the compound, and it multiplies that compound's quantity by whatever factor it's written. For example, 2H2O literally means 2 water molecules. So in a way, we could think of it as there being a total of 4 hydrogen atoms and 2 oxygen atoms from these 2 water molecules. Now, when writing formulas, keep in mind we have what are called diatomic elements. And the prefix di, means 2. So what are the diatomic elements? These are the elements that when they exist as pure substances, they like to pair up. You don't have them existing as single atoms, but in pairs. So what are the diatomic elements? Well, there are 7. And one useful way to remember them are the term Brinkelhoff. Brinkelhoff, referring to the 7 diatomic elements: bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine. When these atoms exist alone, and when you write them in chemical equations, be sure to write them as diatomic molecules with a subscript of 2. Think of them as ladies when they need to go to the ladies' room. They never can go alone, can they? They always like to go in pairs. Well, these ladies like to stay in pairs as well. Brinkelhoff. Looking back at this equation again, we can see hydrogen and oxygen are 2 reactants, both existing alone in their pure form, were written with the subscript 2. So let's take a look. Symbols will show you how many of each element or compound you have. It'll show you what you have. It'll even show you what state it's in. So you can see how important every part to the chemical equation is. And always remember your diatomic elements. So let's see how you take words and write an equation. First, let's evaluate what we have, how many, and in what state. Underlined, we see what we're given. Aluminum, copper 2 chloride. We end with copper and aluminum chloride. So let's start. We have aluminum. Not a diatomic element, so we simply write Al. Well, we have 2 atoms of it, and it's in the solid form. It reacts with, that means plus, copper 2 chloride. Well, remember when writing the formula for copper 2 chloride, it's not Cu2Cl. The 2 refers to the charge of copper. So we know copper's plus 2, chlorine's negative 1. To balance that out, we need 2 chlorides for the 1 copper. The plus 2 and the 2 negative 1s equal negative 2, and now we have the formula CuCl2. It says we have 3 units of it, and it's in an aqueous form. Now this produces, our arrow, copper, Cu, not diatomic, so just the symbol alone. 3 atoms of that, and aluminum chloride. Again, when we write this compound, we have to balance our charges. Aluminum is plus 3, and chlorine is negative 1. So we're going to need 3 chlorines to balance out with the 1 aluminum. Copper was solid, chlorine is aqueous, and there's 2 units of chlorine. Aluminum chloride, excuse me. So you can see how we take words and can write formulas from those words. Now when describing these coefficients, you're going to see you may be referring to individual atoms or molecules or formula units, depending on the type of bond or what you have. 3CO2 could be read as 3 molecules of carbon dioxide since it's a molecular compound. 2Mg could be read as 2 atoms of magnesium as it is a pure substance. And 4MgO can be read as 4 formula units of magnesium oxide. So that should cover the basics of what you need to know about chemical reactions